This is our ETM 110 final project. This project is being presented by Josh Ferguson, Evan White, and Rob Hilgendorf. The name of our project is Traffic Signal Motor Control Speed, and we've added an optional I'm late for class again race game. The requirements of this project was we must use a VFD to control motor speeds, and the motor had to be controlled remotely and not through the integrated VFD keypad. We had to create a functioning stoplight that cycled through green, yellow, and red, all with a different time delay. And the motor was to run at different speeds depending on the color of the light. During a green light, the motor would run at higher speed, a reduced speed when the light turned yellow, and stop when the light turned red. We first had to create the circuit diagram using the constructor software, and the circuit had to be functional in the constructor software. We also had to create a video describing the design, function, and operation and upload to YouTube. We also had the option to include additional circuitry that would be considered for additional credit. The deliverables upon project completion were the constructor diagram, uploaded YouTube video, wired and functioning practice board, and class demonstration. Here's a list of some of the materials that were required from the project. The VFD that was used was the Allen Bradley. We used a Baldor motor. For the game portion, we also had to include a Omron multifunction counter, a Schneider universal programmable relay, a proximity sensor, and a DC power supply. And to supply power to our control circuitry, we used a PowerTran step-down transformer. We're now going to take a look at the design. We've broke the design down into several stages to make it easier to visualize and see on a single screen. So the first stage we're going to look at is our green light stage, our full speed. For this stage, we've chosen to run the motor at 40 Hertz. In order to do so, there is the inputs on the VFD that need to be satisfied. So we created a table to show us exactly what those inputs needed to be for each stage. So as we were doing the design, we could ensure that we were meeting the requirements. So the VFD input number 1, which is our stop input, requires a 1 on it at all times in order for the VFD to operate normally. Our VFD input 2 for this particular stage requires a 1 as well in order to start the motor when the light turns green. We have programmed in preset frequencies, and for this particular one, we've chosen 40 Hertz, and we've programmed that in as our preset frequency 0, meaning that for digital input 1 and digital input 2, we needed a 0 on both of those, which makes it easy for this stage because we didn't have to do anything. So when we apply power to the board, 240 volts, we get L1, L2, and L3 supplying power to the VFD and powering the VFD. It also supplies power to our step-down transformer, which takes 240 volts and steps it down to 120 volts, which allows us to supply power to our control circuit. When power is applied to the transformer, we get power flowing through normally closed time contact TM1 and lighting our green LED, as well as applying power to the coil of TM1. Once power is applied to the coil of TM1, it begins a 7-second timer that will change the state of our contacts, the timed contacts on TM1 once that timer expires. We also are using an auxiliary contact, TM1, which as soon as TM1 is energized, will close and will allow the 24 volts that's supplied by the VFD to pass through and go into our start run input, which will change our input 2 to a 1, which will get our motor spinning. After the 7-second timer on TM1 expires, the normally closed contact TM1 will now open, and this will shut off our green LED, thus completing this portion of the circuit. Stage 2 is our yellow light half-speed stage. For this stage, we've chosen to operate the motor at 20 hertz. On the first stage, our green light stage, we were operating at 40 hertz, so we cut the frequency in half, which should give a good, very clear visual indication of the difference in speed between a green light and a yellow light. So if we look at the input requirements for the VFD for this stage, not a whole lot has changed, except for we need to be able to slow that motor down. And in order to do so, we need to change from our preset frequency 0 to our preset frequency of 1, which is our 20 hertz signal. In order to do so, we just need to change the digital input 1 on the VFD from a 0 to a 1. From stage 1, we were using TM1, timed contacts, to open up normally closed contact and shut off the green LED. And we have that second contact here, TM1, which would have gone from normally open to closed at that time, allowing power to flow through our control circuit and light our yellow LED, as well as energize the coil for TM2. So the circuit, you'll notice, looks very similar. It's a duplicate essentially of the circuit above, and the same will be true of the next stage. So when coil TM2 is energized, it will start a 10-second timer for the contacts that are associated with that, as well as immediately closing contact TM2, allowing 24 volts supplied from the VFD to be put back into VFD pin 5, which is our digital input 1, which gives us a 1 there and changes our preset frequency and changes the motor speed to 20 hertz. This completes this stage. However, I do want to mention a few things while we're here that I forgot to mention earlier. All of our timed coils, you'll notice, have reset, normally closed reset contact on them. We'll talk about that as we get down into the reset portion, but that is how we continuously cycle this and reset these coils that are energized. As well as you'll see some circuitry here, this normally closed Excel contact, and there was a few others on stage 1, and there will be on the future stage as well, that I'm kind of going to ignore talking about here right now because they're associated with the game portion, and we'll talk about that later. So after TM2, after the 10-second timer expires, the normally closed contact TM2 is going to open and will shut off our yellow LED. It's important also to note that we are keeping the coils intentionally energized, the TM2 coils energized, as we don't want these contacts to go back to their original state. We're using this as an interlock so that as the timer expires during each stage, these contacts stay open and will not allow a situation where we have more than one light on at a time. And this concludes this portion of the stage. On to stage 3. And here we are at stage 3, which is our red light stage. Essentially, we just need to stop the motor by not supplying it frequency. And that was easily accomplished if we look at the table through just changing input 1 from the required 1 for the VFD to operate normally to a 0, which will stop the VFD from supplying power out to the motor. The same as in the first 2 stages. When we shut off our yellow light from the previous stage, the timed contacts TM2 change states. That second contact is here as part of stage 3. The normally open TM2 contact would have closed, allowing power to flow through and light our red light on our traffic signal, as well as energize the coil of TM3, which would start an 11-second timer to change the states of the timed contacts associated with it. Same as above, we have auxiliary contact associated with TM3. However, here it's a normally closed instead of a normally open, which has been allowing us to supply the one signal required for the VFD to operate normally. So here in this stage, when we have our red light turn on, we are going to open that normally closed contact, thus stopping power from flowing through back into the input 1 of the VFD, which will give us a 0 on that input, which will bring the motor to a stop. After the 11-second timer expires on TM3, the normally closed contact will open, and that will shut off our red LED, thus completing this stage of the circuit. Keep in mind here as well, we have this reset contact again that we're going to talk about in the next stage, and then we have some other circuitry that's not covered as part of the normal operation that is required for the gameplay, which we'll talk about later. So on to the next stage. We did it. We made it. We're in stage 4. This is our reset stage. We're using this stage to simply reset everything back to the default settings that we were at when we first applied power to the board. We're using an on delay timer, timed contact TM3 is a normally open contact. It's the second contact on that relay. The first one was used above in the red light stage for opening up to remove our red light. At the same time, when that timer would have expired, this contact would close as well, allowing power to flow through and energize our reset coil. And we talked about it a little bit above, if you can remember back that far. We have a normally closed reset contact attached to all of our relay coils that were energized. At this point, when that reset coil energizes, it will open up each of the contacts, and that will open the circuit, essentially de-energizing the coil and putting all of our contacts back to its normal state. We're back up at the top on the green light, working our way back down to reset stage 4 again. It will continue to cycle this way until you remove power from the board. And at this point, that completes our original initial design, and we're going to move forward and talk about the additional things that we've added. Before we get into the actual game, I just want to talk about a couple extra pieces of hardware that were required in order for us to implement the game. First was, I guess not required, but just aesthetically pleasing, was the tire that we added on to the shaft of the motor, the simulated tire that was added onto the shaft of the motor. We also added a DC power supply that was used to power the counter, as well as the inductive proximity sensor that was mounted on the motor, and a magnet was also mounted on the back of the simulated motor so that we could keep count of the revolutions of the tire during gameplay. As part of the extra hardware, we had the counter and the inductive proximity switch that was wired into the counter as a no contact input PNP transistor, and this shows the wiring for the counter as well as a little bit of the technical data for the inductive proximity sensor. It was a normally open proximity switcher with a PNP output type, and then the electrical connections to hook into the proximity sensor. We used the same DC power supply that we used to power the counter to power the proximity sensor as well. So the game we included in our project is called I'm Late for Class Again. And the scenario is very simple. Is, oh great, I know I set my alarm for 6:30 and now it's 6:55 and I only have 5 minutes to get me to my ETM 110 class. Please help me to get there as quick as you can. So what we've done is we've included a game, and the rules of the game are simply that our traffic signal will operate as it normally did on the first part of our project. But we've included an acceleration or boost button that will increase the motor speed. So our full speed during the green light operation was 40 hertz. This allows you to increase the motor to 60 hertz. So you can press and hold the button to override the automated portion of the car and accelerate to 60 hertz. You can do that during any of the lights. You can press it while you're on green light. You can run through a yellow light at 60 hertz. The objective is to obviously get to where you're going as fast as possible. So you do want to hold that button in for as long as you possibly can. But if you do not release the button before the light turns red, then essentially we indicate with some police lights that you've been pulled over and the boost button becomes disabled for 10 seconds as a punishment. So the car will operate at normal speeds, but you can't actually use the boost again until the cop lights turn off. So obviously you want to maximize the amount of time that you're holding the acceleration button, because the more times that wheel spins, the faster it spins, the more counts that you get on the counter. That's how you score points. So every rotation of the tire counts as a point on the counter. So the faster you can get that tire spinning and the longer you can keep it spinning at that speed, the more points you'll get. And this game is loosely based on somebody that's in this class that's constantly either here right on time or is a few minutes late every night. And I'm not going to mention any names, but so let's just move on to the next slide. Now that you better understand the concept of the game, I'd like to take a look at the circuits that make the game operational. Keep in mind that the rest of the circuits are still operating as we described above. These are just in addition to that. So if we begin by looking at the input table for the VFD, we can see that we need to change digital input 2 to a logic level 1 in order to call up our preset frequency 3 of 60 hertz, which will speed up the motor regardless of whether you're at a green or yellow light, green operating at 40 hertz and a yellow light operating at 20 hertz. You'll see a significant increase in speed. The way we accomplish that is when the accelerator button is pushed, power flows in and energizes the accelerator coil. The accelerator coil then closes, normally open contact, 24 volts from the VFD flows through and into pin 6 on the VFD, which gives us our logic level 1 on digital input 2. Keep in mind that at any point, as long as you're holding the button, then we will continue to operate at 60 hertz regardless of the color of the light. However, if you do let the button go, it will just simply de-energize the accelerator coil. The normally open contact will go back to its original state, and we will begin to operate at whatever frequency corresponds with the particular light that you're at the moment. I do want to draw attention to the timed contact TM4, and we'll cover that in a few slides from now. But that timed contact is used as our interlock to ensure that if you are pulled over by the police at a red light and the 10-second penalty is being applied, that is how we're applying the penalty, by opening TM4, thus deactivating the Excel button. You can push it all you want, but as long as TM4 remains open, it's not going to do anything. It'll never energize the Excel coil. And TM4 is on a 10-second timer, so that's where we get our 10-second penalty for the game. Stage 2 is a very simple one. We only have one component associated with the game, and that is the Excel coil. So if we look at the input table, we can see that nothing has changed, which makes our lives easy. The motor is still operating at 60 hertz. This, of course, assumes that the accelerator push button is still being held in at this time. So when the Excel button is pushed, we simply open the normally closed accelerator contact, which stops current flow up to the VFD pin 5, which just ensures that that logic level on digital input 1 stays at a 0 so that the speed cannot be changed from the 60 hertz. Again, same as in stage 1, if at any point the Excel button is released, this Excel contact would go back to its normally closed state, allowing power to flow through it. Digital input 2 would go to a 0, digital input 1 would go to a 1, and we would call up our preset frequency 1, which is our 40 hertz, which is the normal speed to be operating at the yellow light. We now enter stage 3. In stage 3, the motor is going to follow its normal operation. We are going to allow that logic level 0 on VFD input 1 to stop the motor as it was originally designed. The only thing we're concerned about in this stage of the circuit is just simply to detect that the acceleration button has been held in too long beyond just the yellow light stage and has transitioned into the red light stage. So when the accel button is pushed on up top, our normally open contact will go to a normally closed state, allowing power to flow through and energize coil TM4. Now, coil TM4 is an off delay timer that has two contacts associated with it. One from up above that disables our boost button, and the other one down below that will give us our police signal. That coil has been programmed with a 10-second time delay, which is the penalty that is applied to the boost button. So your 10-second penalty either starts in one of two conditions. When you let go of the accelerator button, that will open that contact back up and shut power off to TM4, which would start the timer, or when we have our normal reset signal and the light transitions back from red to green, that would start our 10-second timer. So you can control when your penalty is applied. So when you do run the red light, the sooner you let off that accelerator button will be quicker that your time delay starts, and the less time that will cut into your next green light. In our final design stage, this is the stage that we're using for the police siren. So what happens in this stage is, if you remember from up above, when we energize the coil on TM4, we've got some off delay contacts. So as soon as that coil is energized, the TM4 contact will close immediately. This will allow power to flow through and energize our programmable relay coil, as well as apply power to the common contact on our programmable relay. We're using the flashing relay starting on delay phase, so that we have this pulsating, switching back and forth between the normally open and normally closed, which when power is applied there, we will get our red and blue flashing on and off, which gives us our police signal. So contact TM4, like we mentioned up above, as soon as power is removed from the coil associated with that contact, that will start a 10-second timer. At the end of that timer, this contact will open back up, shutting off our programmable time delay and shutting off our police signal, which is at the same point that your boost button would be re-enabled. Now that you understand exactly how the circuit works and how it was intended to function, let's take a listen to Josh and let him show us the circuit in action. This is just the normal portion of the circuit without the gameplay.
This is our circuit. As you can see, it cycles through green, yellow, red, and the motor controls the hertz on here. You're going full speed, you slow down to 20 hertz, and then the red would be like stopping at a stoplight.
Thank you, Josh, for that. And now Evan will walk us through the circuit with the gameplay mode installed.
So the objective of our game is to get the highest points possible. For every revolution of the wheel, you get one point. As the wheel spins, a magnet activates the proc switch, and your points accumulate. During your normal cycles, so during the 40 hertz, you're obviously going the speed limit. Yellow, you'll slow down, and then red, you'll come to a stop. We added a boost button to increase your score at any time during the green and yellow cycles, but don't run a red light or risk getting pulled over by the cops. At this point, you're unable to go anywhere or use your boost until the cop lets you go.
I promise you, it's really over now. There's no more slides. But thank you for taking the time to watch our video, and we hope that you have enjoyed it. Unfortunately, we had to disassemble some of our circuit because we had pieces of the hardware that had to be brought back to the people that we had borrowed them from. But the basic part of the game is still operational. It's just that there will be no counter for the points accumulation. But if you want to check it out and see how it worked, you can stop by our board and take a look at it. Thanks.